Hello students, this is a short video on nucleophilicity versus basicity. It's a very important concept from General Organic Chemistry GOC. First, let's understand what is the difference between nucleophile and a base. In general, a nucleophile is any negatively charged or neutral species having a lone pair, and its ability to donate the lone pair decides its strength. But when we talk about a negatively charged species, for example, let's consider OH-, then the negatively charged species in chemistry can act as a nucleophile or a base or a ligand. We will talk about ligands in coordination compounds, but as of now, we are comparing a nucleophile and a base. Now, it's a well-known fact that when we talk about OH-, the first thing that comes into mind is NaOH, and it's a strong base because it comes from alkalis family. But OH- even can act as a nucleophile. So what is the difference? Nucleophile is a species which donates its lone pair to carbon atom, whereas base is a species which donates its lone pair to the hydrogen atom, more specifically to the H plus ion. Here you can see there is ethyl chloride or chloroethane, wherein carbon to chlorine bond is polarized due to difference in electronegativity. And now the OH- can attack the positive charge of the carbon atom, and here when it attacks a positively charged carbon, it will act as a nucleophile. But when the same OH- is added to the phenol having the acidic H, so the H plus can be removed by the OH- attack. So here the OH- when it attacks the H plus will act as a base. Next important thing, nucleophilicity is a kinetic concept, meaning it deals with the rate or speed of reaction, and basicity is a thermodynamic concept, meaning it deals with the stability of the species formed. What does it mean? When the OH- is attacking the carbon of the chloroethane, how fast it attacks the carbon atom will be decided by the groups attached to the positive center of the carbon atom. If the number of groups attached are bulky or more, then the attack of this OH- would become difficult and the reaction would take place slowly. So in this case, the kinetics of the reaction would be slower. But when the OH- is considered, it does not deal with the steric factors, or it is not dependent on steric factors. In fact, it is related with how fast the H plus could be detached from the OH of the phenol. So, when the H plus is broken down, the amount of enthalpy or heat required to separate this H plus would be determined by the thermodynamics of the reaction. So that's the reason we say that nucleophilicity is a kinetic concept and basicity is a thermodynamic concept. Coming to the next point. Nucleophile is dependent on steric factors, whereas base is not. This is just what I said. Nucleophile is dependent on steric factors, meaning it is related with the kinetics of the reaction, whereas base is not dependent on steric factors of the acid. That is why it is the thermodynamic concept. Nucleophilicity. The term nucleophilicity means the tendency of a nucleophile to donate the lone pair. So how easily the lone pair is donated would decide the strength of the nucleophile, and that is what is called nucleophilicity. So we have the examples wherein the nucleophilicity or nucleophile strength is being compared. So first example, OH- versus H2O. Now, if you look at OH-, it is a conjugate base of the neutral water molecule, and water being a weaker acid, its conjugate base is very strong. So when a negatively charged conjugate base is compared with its acid, the base is going to be always stronger if the acid is weaker. So in that case, the nucleophilicity parallels basicity. Parallels basicity means the nucleophile ka strength and the base ka strength would be similar and there will be no difference. So a simple conclusion to this is the nucleophile strength is dependent on the amount of negative charge. When a negatively charged species is compared with its corresponding neutral species, then of course the electron density on the negatively charged species would be higher, so its tendency to donate lone pair would be higher and its nucleophile strength would be also higher. Similarly, the methoxide versus methanol. Methoxide is a strong conjugate base of a weaker methanol, and since nucleophilicity parallels basicity over here, the methoxide would be a stronger nucleophile than methanol. Next is a very important comparison: methoxide, phenoxide and acetate ion. If I talk about their corresponding acids, first I'll just compare basicity, then I'll come to nucleophilicity and we will see whether it parallels or not. Methoxide is a conjugate base of methanol. Phenoxide is a conjugate base of phenol. Acetate is a conjugate base of acetic acid. Now, among the organic compounds, acetic acid is a very strong acid as compared with phenol and very strong in comparison to methanol. So, we can conclude that acetic acid is the strongest acid, hence its conjugate base is going to be weakest. Methanol being the weakest acid, its conjugate base would be strongest. So, if I talk about the basicity or basic strength, methoxide is a stronger base than phenoxide than acetate. Now, when I talk about nucleophilicity, I have to just simply compare the tendency to donate lone pair. For that, I'll look at the electron density on the negatively charged oxygen. Methyl is electron donating group. So, as an EDG and the plus I effect, it will increase the electron density on oxygen. In case of phenoxide, the lone pair gets delocalized due to resonance, hence the intensity of the negative charge would be decreased over here. Acetate ion also have pi alternate lone pair in conjugation, due to which the negative charge here gets distributed equally as minus half, hence the intensity of the negative charge is decreased to a larger extent in acetate as compared to phenoxide. So from this discussion, I can say that the negative charge on oxygen is highest in case of methoxide and hence the tendency to donate the lone pair would be highest for methoxide. So methoxide is a stronger nucleophile than phenoxide and then acetate ion. So again here nucleophilicity parallels basicity. Next we have the comparison of hydrogen peroxide with water. Now firstly, I'll compare basicity and then compare the nucleophilicity. Peroxide, because it has two H plus ions and after the donation of two H plus ions, the O2 2 minus is very stable anion formed. That's why peroxide is a stronger acid than water. Peroxide being a stronger acid should be a weaker base as compared to water. So as per the basic strength, the peroxide is a weaker base as compared with water. But when we compare nucleophilicity, peroxide is a better nucleophile than water. Remember, here the nucleophilicity doesn't parallel basicity. In fact, it is the reverse scenario. So peroxide, why it is a stronger nucleophile? We know that peroxy compounds are joined with oxygen, single bond oxygen. Since the bond length of this compound is very short, the lone pair on the two oxygen atoms repel each other. Because of the repulsion, the donation of the lone pair becomes easier. So peroxide has higher tendency or easier tendency to donate the lone pair than water, and that's why it's a better nucleophile because LP-LP repulsion in peroxide is higher. Same goes with hydrazine versus ammonia. The nitrogen-nitrogen single bond has a short bond length, and because of the NN repulsion, the LP-LP repulsion, the donation of the lone pair is easier, and hence it's a better nucleophile. Next is very important comparison. We have the alkoxide ions to be compared. The first is ethoxide, second is isopropoxide, and third is tert butoxide. Once again, first I'll compare the basic strength or basicity. So for basicity, best is to compare the acidic strength. So ethoxide is the conjugate base of ethanol, isopropoxide, isopropanol, or 2-propanol or propan-2-ol, and tert butoxide, tert-butanol, or 2-methyl-propan-2-ol. Now, in terms of acidic strength, methanol is the strongest acid, and as we go to secondary and tertiary alcohols, the acidic strength goes on decreasing. So, ethanol is a strong acid, that's why its conjugate base, ethoxide, should be very weak. So, in terms of basic strength, the ethoxide is a weaker base as compared to isopropoxide, as compared to tert butoxide, meaning tert butoxide will be a very strong base. But when we compare the nucleophilic strength or nucleophilicity, the trend is again reverse. Meaning here also nucleophilicity doesn't parallel basicity. Why? As I said earlier, that nucleophilicity is a kinetic concept. So as the bulkiness of the groups attached increases, the strength of the nucleophile decreases because its ability or tendency to attack on the positive center of the electrophile would become difficult because of the steric factor. So here ethoxide would be a better nucleophile than isopropoxide than tert butoxide. But in terms of basic strength, tert butoxide would be a very strong base as compared to isopropoxide as compared to ethoxide. So in this example, nucleophilicity doesn't parallel basicity. Now we come to a very important section, the nucleophilicity comparison in different types of solvents. So I have taken two cases over here which are very important. The case 1, the strength of the nucleophile in polar protic solvents, and case 2 in polar aprotic solvents. First, I'll focus on the explanation of polar protic solvents. So, from the name itself, polar protic solvents are those solvents which are polar in nature and have a tendency to give away the H plus ions, that is proton. So water or ethanol are good examples of polar protic solvents because both have the polar OH group and that can be broken down, and the H plus ions could be generated in the aqueous form. Polar aprotic solvents are polar solvents, but they do not have the tendency to dissociate or break down the H plus ions. Acetone, dimethyl sulfoxide, shortly called DMSO, or dimethylformamide, shortly called DMF, or even acetonitrile, that is methyl cyanide CH3C triple bond N, are good examples of polar aprotic solvents. So firstly, polar protic solvents are polar solvents having a tendency to cover away H plus ions. Examples: water, ethanol. And polar aprotic solvents are polar solvents but no ability to give H plus. Example: acetone, dimethyl sulfoxide DMSO, dimethyl formamide DMF, and acetonitrile, that is CH3C triple bond N or methyl cyanide. Having understood this, when we talk about the strength of the halides, nucleophiles, in the polar protic solvent, the order is fluoride is the weakest nucleophile, followed by chloride, bromide, and iodide. Meaning, if I talk about the trend from top to bottom, the nucleophilicity goes on increasing in polar protic solvent. But in polar aprotic solvent, this nucleophile strength is reversed, meaning from top to bottom now it goes on decreasing. Let's understand why is the trend reversed when the solvent is different. When I talk about polar protic solvent, the focus is on H plus ions, and these H plus ions have the tendency to form H bonding with the anions of the halide ions. So, as we know that fluorine is the most electronegative element of the entire periodic table, so the negative charge on the fluoride would be more concentrated, due to which there will be more of H plus ions surrounding the fluoride ions. The other reason is also its small size. So the F minus ions would be solvated more by the H plus ions. So because of more solvation, the tendency to donate lone pair would be very less. But if I talk about iodide, because of the bigger size and a lesser intensity of the negative charge, it would be less surrounded by the H plus ions. So now its tendency to donate lone pair would be very high. So iodide is a very good nucleophile in polar protic solvent. So let's see the reason. Due to more water molecules surrounding the F minus ions, thereby increasing nucleophilicity down the group. Nucleophilicity increases down the group in polar protic solvent. But in case of polar aprotic solvent, let's analyze acetone structure. Acetone is dimethyl ketone, so we have two methyl groups and a carbonyl C double bond O, which is polar in nature because of the difference in their electronegativity. Carbon has delta plus and oxygen has delta minus. Understand this structure very well. Here I am saying that the delta plus of acetone is hidden, meaning it does not want to interact because this carbon is surrounded by two methyl groups and the negatively charged oxygen. So this delta plus of acetone is hidden and it does not want to interact. But if I talk about oxygen, it is in the outer part, so it is exposed, and because of the exposure and a higher amount of negative charge, it will have the tendency to repel other negative charge. So now, out of these halide ions, the F minus has a very high intensity of negative charge. So this negative charge would be repelled more by the exposed negative charge of the acetone. Similar is the case for dimethyl sulfoxide, dimethyl formamide, or even acetonitrile. So because of the higher repulsion, the tendency to donate lone pair here would be higher for fluoride, and down the group it will go on increasing. So the factor in polar aprotic solvent is the repulsion with the exposed negative charge, but in the polar protic solvent it is the solvation by the H plus ions of the highly negatively charged species. So reason here is F minus would repel most as its electron density is very high and hence would donate the lone pair easily. So a simple conclusion from here, the nucleophilicity increases down the group in polar protic solvent, but the nucleophilicity in polar aprotic solvent decreases down the group. So same if I compare for the group 16, the methoxide versus methyl thioxide. Again, the negative charge on the oxygen is more concentrated as compared with sulfur because of more electronegativity of oxygen. So when I talk about polar protic solvent, I'll consider the solvation. So this O minus will be more solvated, so its tendency would be less, so it will be a weaker nucleophile. Hence, methoxide is a weaker nucleophile than methyl thioxide. But when I compare this in polar aprotic solvent, I have to look at the exposed negative charge and the repulsion. So this O minus would repel more and the tendency to donate lone pair would be higher. So methoxide is a better nucleophile than methyl thioxide in a polar aprotic solvent. Same will be the case if I compare group 15, Nicogens family, NH2 minus versus PH2 minus. Lastly, I have CH3 minus the carbon ion versus NH2 minus, amide anion, oxide -2, and fluoride. So here I have to compare the electrophilicity. Here I have to compare nucleophilicity. So nucleophilicity is a simple tendency to donate the lone pair. And here, when the negative charge is on different atoms, we have to just compare the electronegativity. As the electronegativity increases, the negative charge would be more concentrated on it, and the tendency to donate the lone pair would be lesser. So, in case of carbon bearing a negative charge, it has a lower electronegativity. So, the negative charge will be less concentrated here and tendency to donate would be higher. So, as the electronegativity increases from left to right, the nucleophilicity decreases. So, across a period, the nucleophilicity decreases as the electronegativity goes on decreasing. A very important point to be noted: basicity does not depend on the solvent, as it is a thermodynamic concept. Meaning, if I compare the basic strength in polar protic solvent or polar aprotic solvent, the basic strength ka order is not going to change. It's going to remain same, meaning it is independent of the type of the solvent. Because it's a thermodynamic concept, it just deals with the easiness of the breaking of the H plus ions of the acid.